In this video, we're going to discuss the molecule of water. Now, in our class up to this point, we have not used the term molecule. So water is H2O. But when we look up water on the periodic table, what we find out is that, well, not water on the periodic table, but hydrogen and oxygen. Hydrogen is a non-metal on the left side of the periodic table. And, excuse me, hydrogen is a non-metal. It's on the left side of the periodic table, but it really belongs on the right side of the periodic table. On the left side of the periodic table are all the metals like zinc and silver and gold. But hydrogen on the left side with the metals really belongs on the right side with the non-metals, but we have to put hydrogen in column 1A because it has one outer electron. So the only column we can put it in is 1A, but we just have to realize even though hydrogen's on the left side with all the metals, it is a non-metal. Oxygen on the right side of the periodic table is also a non-metal. So when we analyze H2O, hydrogen is a non-metal and oxygen is a non-metal. We have not studied two non-metals sticking together or connecting or bonding. When non-metals stick together, what they do is they do not transfer electrons, they share electrons. And by sharing electrons, they do not make ions. They do not make large ionic crystals of repeating patterns of positive and negative ions like metals and nonmetals make. By sharing electrons, they make what are called molecules. This is the molecule of water. And I think we would all agree that this structure that we get when we have two nonmetals connecting, the oxygen and the hydrogen, two H's and one O connecting, this molecule looks very different than this repeating pattern of positive and negative ions making an ionic crystal. Here you have a metal and a nonmetal. The metal is losing its electrons to the nonmetal, making a large ionic crystal. Here you have two nonmetals that are sharing electrons, making individual molecules. Now, one of the things that's unique about oxygen being connected to hydrogen in this form is that they are sharing electrons. This line and this line, this gray stick and this gray stick, represent the shared electrons. Those are the shared electrons, and that's what makes the connection. Here, in an ionic compound, the connection is formed from the opposite charge of the positive and the negative ion because the metal has lost the electrons to become positive. The nonmetal has gained the electrons to become negative. Here, they're sharing electrons. But the unique thing about water is there is what is called unequal sharing taking place. Not all molecules have unequal sharing, but water does. So what happens is these electrons that are being shared actually get pulled toward oxygen because oxygen's a little stronger in attracting electrons. How do we know that? If we go to our electronegativity chart, this is the attraction for electrons. Oxygen has a 3.5 0.44 value for attracting electrons. Hydrogen has a 2.20. So oxygen's stronger in attracting electrons. So even though they're sharing electrons, oxygen pulls them a little bit closer. You've seen kids sharing things before, and maybe one of the kids is pulling that toy a little bit closer to itself. Well, that's what's happening with oxygen. Even though these electrons are being shared, they get pulled toward oxygen. Because of that pulling, what happens is this side becomes a little bit negatively charged. Not an ion completely negative, but a little bit negative, and this side becomes a little bit positive. This sign here means partial. So this sign equals partial. So we would say partially negative, a little bit. Partial just means a little bit negative, and a little bit positive because of the unequal sharing of the electrons. Now, this is important because now, when you take an ionic compound like our MgCl2 or like our MgO from the lab, and these are negatively charged and these are positive, and you put it into water, which has a partial negative charge and a partial positive charge, a little bit negative and a little bit positive. Why is that? Because they are sharing electrons, but they're unequally sharing. So those shared electrons move towards oxygen, creating what we call this not just a molecule, but we're going to call it a polar molecule. Polar molecule. Polar means it has a little bit of a negative side and a little bit of a positive side. When you place this ionic compound into a polar molecular substance, the negative side is attracted to the positive ion, and the positive side is attracted to the negative ion. And the positive comes in and pulls and tugs on the negative ion until finally it pulls it away. And the negative side, another molecule, comes in and pulls and tugs until it pulls the negative or the positive ion away. So the negative side is attracted to the positive, and the positive side is attracted to the negative, and you get millions of water molecules bombarding the surface of this ionic compound, and these water molecules grab the ion, the individual ion, and pull it away. That process is called dissolving. So dissolving equals the ionic compound with positive and negative ions being pulled apart, by the polar water molecule. And that is dissolving, and that's what happened at the end of the lab when we took our MgO, which involves an Mg2 plus and an O minus, and we placed it into water, and the water came in and pulled it apart. It dissolved. How did we know that it dissolved? The dissolving process produces individual positive and negative ions, produces individual positive and negative ions surrounded by water molecules. Those individual positive and negative ions were measured by the conductivity meter. By having all those blinks on the conductivity meter, it indicated that there were individual positive and negative ions. And I'm going to include the word ions in there. Individual positive and negative ions surrounded by water molecules. How did we check for ions? That's our conductivity meter checks for ions. I hope this helps understand the dissolving process and water being a polar molecule causing the dissolving process to take place with an ionic compound.